In this section, we're talking about the continuity equation and Bernoulli's principle, and both of these deal with what we refer to as ideal gases. An ideal gas has three parts to it, three things that make it an ideal gas. The first thing that makes something an ideal gas is that it is a laminar flow. Another name for laminar flow is that it is streamlined. Now, the opposite of streamline is turbulent. So, if that helps, it is the opposite of turbulent. To be laminar means that every particle that passes a particular point moves along the same smooth path traveled by the particles that passed that point earlier. In other words, it is predictable. We know the path of each particle because it moves moves right after the one that came before it. The second thing that makes something an ideal fluid is that it is incompressible. Now, of course, everything can be compressed a little bit, but it's as close to being incompressible as possible. And the third thing is that it has a low viscosity. Viscosity is the thickness of a fluid. And so we want fluids that are very thin, things like water or air, not things that are thick like honey or molasses or something like that. So it needs to flow really easily. We say that it has no internal friction. So the particles have no friction with each other, and they have no friction with the outside walls of the pipes. So what can we gather from these ideal fluids? Well, what we want to do is calculate what we refer to as a continuity equation. That means what stays the same as a fluid moves from a pipe of one section to a pipe of another, a second section. Now, because this is an incompressible fluid, we know that the volume of the first section is equal to the volume of the second section. Something like, let's say, water. So volume of water does not change as we move it from one container to another or one section to another. We're going to divide these by time. We're going to talk about something referred to as the flow rate. Volume over time is called the flow rate. And this is measured in units of meters cubed per second, or any volume divided by a time. Now, the volume of this section of fluid is equal to the cross-sectional area times its length. And so I'm going to replace volume with area times the length, still divided by the time, and replace the second volume with area times the length, and again still divided by the time. Now, distance divided by time, we know from earlier this year, is the speed. So the area times the speed of the first section of fluid in the pipe is equal to the area times the speed in the second section of the fluid. This is what we refer to as the continuity equation. And we see that the area times the speed is the same as that volume times the time. So it is also the flow rate. An example of this, we can see as it gets to a second section, the area has gone down in the second section. And so to compensate for that and keep this value the same, this product the same, the speed in the second section must go up. We've all experienced this when we put our thumb across the opening of the garden hose. We decrease the area and therefore increase the speed of the water coming out of the hose. However, the volume coming out of the hose every second stays the same. Even if we put our thumb over the edge, the water's coming out faster, but the amount of water coming out of the hose each second stays the same. So it's not going to fill a bucket any faster if we put our thumb over the nozzle. It'll still fill the bucket in the same amount of time. The volume per unit time is the same. Now I want to talk about Bernoulli's principle. Conceptually, Bernoulli's principle says that as the speed of the fluid increases, pressure within the fluid decreases. So as the fluid moves faster, the pressure drops. So as the speed goes up, the pressure goes down. And likewise, as the speed goes down, the pressure goes up. Now, objects always move towards lower pressure, which is why when we have like a lawnmower, the lawnmower makes the blades move faster, so it moves the fluid, the air above the grass fast, and that's going to drop the pressure, and objects always move towards lower pressure. In other words, they move towards a faster moving fluid. That's why tornadoes that are moving fast, objects move towards the tornado. Windows blow out of a house towards the tornado. A spray bottle, as you squeeze the trigger, it moves the air moves fast at the top of the nozzle, and the fluid moves up and towards the nozzle. Now mathematically, we see it as this relationship here, which says that the pressure plus 1/2 the density times the speed squared plus the density times gravitational field, 9.81, times the height stays the same. That whole amalgamation stays the same from location to location. So we see as the speed goes up, the pressure goes down to compensate for that.